Hi all, and thanks for attending this quarter's edition of Security Observability Day. We're super excited that you could be here with us for this short discussion on how you can enhance your security posture using just some of the tactics, techniques, and products we create here at Datadog. Keep the questions coming in the chat. After all, this is a live event, and we want to hear from you. You'll want to direct those questions to the Q&A feature in Zoom and not the regular chat. But no question is too big or too small for us to answer. Any questions that we don't have time for will get answers via email after the session. We're going to do something just a little differently today. You'll learn what some of the concerns are for building in cloud. You'll learn how we think about detection engineering as it relates to the 4 major baskets of cloudy components. And you'll also get a product demo of one of our latest blocking capabilities in the ASM product. And we'll even share with you a little about an almost security incident we had inside of Datadog. I'm, of course, joined today by just a few colleagues who I'll let introduce themselves as they come on screen. Over the course of the session, do feel free to direct questions to Anthony, Camille, Jules, or of course myself. By the way, I'm Andrew, and I lead the security advocacy team here at Datadog. We may have met at one of our great events, conferences we sponsor, or you may have enjoyed some of the content that we write on Datadog Security Labs. As cloud practitioners, you're presented with more options to build, deploy, and operate cloud resources than ever before. And while this can be an accelerator for your business and your feature delivery, you may not be aware that this increased diversity in environments can lead to blind spots in your observability and security of your applications. These blind spots can be everywhere through the stack. They can come in the form of misconfiguration that gives access to your data plane, an exploited workload that allows theft of your compute impacting performance, or they could come in the form of a threat like an SSRF, where credentials are leaked from the environment and then leveraged for additional reconnaissance or moving deeper into infrastructure and data. Due to the nature of cloud, the same features that allow you to build at the speed of business are also accelerators for attackers. The agile and flexible nature of API-driven infrastructure can result in devastating impact to your business over time. Truly, as an industry, we can't afford to continue to accept the status quo when it comes to detecting and responding to threats in the cloud. And if you're wondering what that status quo is, according to Forbes, dwell time, or the time between an attacker accessing an environment and being detected, is actually going up. In fact, in the last 2 years, it's risen from 70 to nearly 100 days. Of course, in order to be effective, we need to beat this by quite a bit. Minutes, not days, should always be the goal for mitigating a cyber attack. In just a moment, you're going to hear from one of our detection engineering managers on how we think about detecting across the cloud to lower that metric.
Thanks, Andrew. Hi, everyone. I'm Anthony Randazzo, and I lead our detection engineering team here at Datadog. We're responsible for building the detections that surface actionable security issues to customers and our security platform. I'm here to share how we conceptualize building those detections to find threats that matter most. To begin, let me introduce the 4 C's of cloud-native security. This is a layered defense in depth approach to securing our applications in the cloud. As we saw just a moment ago, there's a complex ecosystem in the cloud today. But if we can think about this complexity in 4 distinct layers, we can then apply security controls at each layer, and it's much easier to get our arms around. These layers are code, container, cluster, and cloud. We'll spend much of today talking about how to identify these blind spots shown before in each of these layers. As I mentioned, we can approach cloud-native security by applying security controls at each of the 4 layers. However, there's different security controls we have to consider. We can apply preventative controls, such as the use of temporary credentials versus long-lasting permanent credentials, or ensure least privilege in our identity and access management policies. Preventative controls keep security issues from occurring in the first place. We also have corrective controls. These are generally fixes applied after an issue has surfaced, such as remediating a vulnerability or using data backups. Lastly, we can deploy detective controls. Detective controls are where we'll focus our attention today. These controls are where we can instrument a variety of data to detect security issues such as misconfigurations, vulnerabilities, and threats in our environment. Here at Datadog, we leverage our 3 pillars of observability data to detect these security issues. This includes infrastructure monitoring and metrics, application performance monitoring traces, and log data from up to hundreds of technology integrations. Our detection engines consume this observability data and then feed security signals into our different security products on our platform, namely our application security, cloud security management, and cloud SIEM suites. Security signals are the outputs from the data that processes through our detection engine logic. In fact, we can take this mental model of detections in the observability data across the 4 Cs and see how they actually line up against our security products today. Now, let's consider detection relative to the DevOps lifecycle we're all familiar with. DevSecOps layers on security processes throughout the application development. So where does security detection happen in this lifecycle? Because we cannot necessarily detect threats early in the DevOps lifecycle, we'll need to continuously monitor for those blind spots while our application is in production. All of the examples you'll see today are real threats we've detected across our customer base against their production environments. None of that simulated stuff from a lab environment. Now, let's start with our first C of cloud native security, code. This is where we, as organizations, have the most control over security. We can perform static, dynamic, and interactive application security testing against our code. We can also scan for vulnerable packages through software composition analysis. But what about when we ship our code to production and our application's accessible to the world? Let's dive in to how we can monitor our application and detect threats in real time. At Datadog, we're able to leverage the distributed tracing instrumented directly from our code at runtime and our APM platform to provide context-aware threat detection. This helps teams understand how an attack flows through our services, a level of granularity which enables faster investigations and response. This level of observability isn't even possible with perimeter application firewalls because they can only inspect an incoming request without any additional context of the destination application. Here we can see a real SQL injection attack by looking at the payload and the traces. Because we're able to see the application's response to certain inputs, it looks like this malicious payload was able to successfully execute a request to the data store in the service chain. And because no errors returned, this increases our confidence that this may be a successful attack. We can dive further into some of the existing observability data within APM to identify the scope of this particular attack. We can see this has been ongoing from this particular IP address for several days, and that it's likely a known web scanner performing these injections thousands of times. Let me introduce Camille Fabregat from our Application Security Engineering team to talk about how you can use IP blocking and application security management to prevent these attacks once you identify a threat like this.
Thank you, Anthony. Hi, my name is Camille Fabregat, and I'm an engineering manager here at Datadog. Today, I'm excited to showcase how you can use application security management to protect your web applications efficiently and at scale, whether they are APIs, microservices, or serverless applications. As a reminder, we have a live chat where you can ask any questions if you're curious about anything I present. Now, let's dive in. Let's start with traditional perimeter-based web application firewalls, or WAFs. They leverage pattern matching-based detections, which work well against known attack patterns. However, when production systems are composed of layers of microservices, a traditional WAF cannot drill down through them. As such, they can't differentiate between trusted requests coming from an internal service and untrusted requests coming from an external source. This lack of granularity means they cannot identify and alert you of malicious traffic at an early enough stage, and often that can lead to missed threats. One example is business logic abuse attacks that can go undetected. Finally, Perimeter WAFs cannot tell how the application will process data, and WAF operators can often experience a high false positive rate. Oftentimes, their WAFs will even stay in monitoring mode, leading to attacks not being stopped at the edge and making their way into the applications. That's where Datadog's Application Security Management, or ASM, comes in. ASM sits within the application rather than on the edge, which allows it to provide stronger detection accuracy and more efficient blocking capabilities. Out of the box, ASM's in-app WAF can detect 140 types of attacks, such as SQL injections, server-side request forgery, and cross-site scripting. After the initial setup of ASM, you might see a lot of activity from scanners targeting your web applications. This shows that ASM is indeed well monitoring your traffic. These scans can already be detected by traditional WAFs and are unlikely to cause real issues, but they could be reconnaissance scans from attackers. Let's say that an attacker performed one and learned about an SSRF vulnerability in your system. So this is our SSRF signal. Let's respond to this signal together. You can block the IPs that triggered this signal in just one click here. And here, ASM has also detected an authenticated account involved in the signal. We recommend also blocking it, as IPs can be easily spoofed and attackers can just rotate their IPs and attack their services again. You can also configure ASM to automatically block IPs and users involved in any new SSRF signals, temporarily or permanently. Let's go ahead and confirm we blocked the IPs involved in the signal. So we see this IP that was involved in the signal is now blocked. As ASM's in-app WAF can leverage the runtime context, it can determine whether or not an attack was successful and if it can really lead to a breach. The level of accuracy this provides enables ASM to secure your application assets with peace of mind. Here, the same attacker has unfortunately successfully managed to trigger a vulnerability. ASM will immediately prevent their subsequent requests. And on top of that, ASM will provide all the required context for you to fix the issue as soon as possible. So here, if we scroll down, we see exactly what endpoint was compromised, and we can navigate to the endpoint catalog to learn even more about this endpoint. Finally, if you want to block IPs over all your existing infrastructure, you can also use Datadog's workflow automation product. IPs will be blocked for your existing WAF provider. Let's take this very simple workflow, for example. It extracts malicious IPs from the signal and synchronizes them with your WAF. If you're using any other WAF provider, this is configured for AWS WAF, you can easily edit this workflow and you can also extend it to match your organization's needs, add Slack notifications, create follow-up security incidents, and so on. I've already configured this workflow with my WAF provider details. Let's now go and run it from a security signal. The same SSRF signal we had before. So I'll go here, click Run Workflow, run it in a few clicks. I can follow the execution of the workflow in this tab, click here for more detail. And now we see the workflow execution has completed successfully and the IP has been blocked at the edge. Now, beyond generic vulnerabilities, ASM's unique position within the application allows building detection rules tied to the application's business logic. Popular use cases include detecting excessive account creations, deletions, or password reset attempts. Another popular use case is detecting credential stuffing attacks or account takeovers. In these, attackers steal your users' credentials, compromise their accounts, and in turn potentially breach into your systems or steal sensitive data. Let's dive deeper into one of these. Here, we see 11 IPs are involved in a brute force attack against the admin account. They have been triggering thousands of unauthorized errors before finally managing to log in, which means user accounts were successfully compromised. A traditional web application firewall may not be able to monitor privileged accounts, leaving them vulnerable. But with ASM, same as before, you can automatically block both the attacking IPs and the compromised accounts. Going forward, leveraging Datadog's SDK, security teams and application owners can also collaborate to create custom detection rules, truly monitoring the service's own business logic, and preventing attackers and fraudsters from abusing it. All it takes is mapping key business events in your service's code base and creating custom detection rules monitoring them. And as for out-of-the-box detection rules, custom ones can also trigger protection countermeasures against any attackers. Let's recap what we just saw. ASM can detect attacks through generic vulnerabilities or business logic abuse with high accuracy and protects against malicious IPs and authenticated users in an automated fashion. Now let's see how this unique approach to protection can scale up to thousands of web services composing your production systems. Let's start with our in-app WAF configuration, where teams can apply policies to scale their protection configuration to thousands of services. Datadog ASM offers an out-of-the-box recommended policy updated every month by Datadog's threat detection engineering teams. For finer-grained control, you can also create custom ones. These can be scoped down to the environment and service level while distributing the security ownership across teams. If you remember, previously, an SSRF vulnerability was triggered on your web store service. So you can create a custom policy to set all SSRF rules to blocking mode on this service specifically. And to go further, you can also create custom in-app WAF rules to monitor events on specific services and apply virtual patching to vulnerable paths. Now let's go and take a look at all your production services at one glance. This is the service catalog. It provides a 360 view of all your services, ownership, reliability, performance, and security posture. From there, it's easy to identify at a glance which services have critical or high vulnerabilities or are exposed to attacks. Leveraging one-click activation, you can add ASM to your services without any required software updates or introducing any new agents. In conclusion, thanks to its in-app and decentralized model, ASM is providing high-accuracy threat detection and distributes security ownership across the stack. It enables both security teams and application owners to easily set up, scale, and automate the protection of their production systems up to thousands of web services. And now, within the same product they already use for reliability and performance, engineering teams are empowered to secure the stack they own. I'll hand it back to Anthony to talk more about the 4 C's of cloud-native security.
Thanks, Camille. Now that we have an idea of how we can detect and protect from threats against our code at runtime, let's continue our journey through the 4 C's of cloud-native security and talk about containers. Containers are generally the lowest level of infrastructure we interact with in our cloud environments. This is where our application code is running. If we recall the various types of security controls, we can apply many of those at this layer too. For example, we need to detect and remediate critical container image vulnerabilities, or ensure secure configurations to our Docker deployments. However, once our code is in production, we'll want to continuously monitor and detect for threats at runtime in our containers. At Datadog, we can accomplish this by enabling cloud workload security on our Datadog agent to collect workload data via eBPF. Once we collect that data, we'll process and enrich it through our detection engine described earlier to surface threats to investigate in the Datadog platform. Here, we have a security signal from our cloud workload security for a potential crypto miner running on our workload. We have the full process context, which helps us paint a picture of what may have happened. We see the miner process with the Stratum proxy arguments, which is a mining protocol, as well as the Tor socks process used to anonymize this host in the mining pool through the Onion routing anonymizing network. Further up the process lineage, these appear to be the result of some insecurity in this container's Python utility. When we layer in the existing observability already available in the platform from our infrastructure monitoring products included in the core Datadog agent, we can see huge CPU spikes indicating resource abuse from the mining process. We even see the signal plotted on the CPU timeline. We're ultimately able to drive up confidence that this is in fact a compromised piece of infrastructure and not a false positive. Our next layer in the 4 C's of cloud-native security is cluster. This is where we also need to apply those technical controls to protect our orchestration layer over all of those containers running our application. We can apply preventative measures to our Kubernetes clusters like strong authentication and authorization, good practices for secrets management, and secure network policies. But like we discussed in the other cloud-native layers, we need to ensure we're focused on detecting threats in the production against our cluster as well. In this example, we're able to process the existing network performance monitoring data already available from the infrastructure observability to identify exposed Kubernetes APIs and the network traffic in our cloud workload security product. While this is disabled by default in the latest Kubernetes version, it was found that there were nearly 400,000 publicly accessible Kubernetes APIs just last year. This context associated with this signal tells us that we had 4 unique external IPs communicating with this host over server port 10250. Our infrastructure observability allows us to triangulate and determine that this is in fact a Kubernetes API for version 1.26, and it's likely exposed over the internet, given that we can see an enriched IP address, enriched IP traffic to a known malicious IP. Since this was one of the most current versions of Kubernetes, this was probably a post-deployment misconfiguration on the user's part. So now that we've talked through some of the pieces of data we can use for individual detections, but the real advantage comes when we take all of these data sources and use them to correlate and enhance detections using as many of the 4 C's as possible. To showcase just one example, we brought a very special guest from the security engineering team to tell you about a real-world security investigation we performed here at Datadog.
Hello everyone, my name is Jules Denardou. I am a senior security engineer at Datadog, and today I'd like to talk about how we use Datadog to detect an attack attempt on our Synthetics product. For that, I will go through an investigation we did following a detection made by the product. The investigation started at 3:14 p.m. We investigated the signal, gathered information around the attack attempt, and were able to conclude and remediate at around 6:44 p.m. During the day, Datadog detected that some of our Synthetics workers' servers were connecting to penetration testing domains. Automatically, a signal was created, and we were notified by it. This signal will show us which server is affected, the logs related to this signal, and potentially related signals. From there, we can directly start the investigation and open an incident channel to collaborate with the rest of the team. At 3:14 p.m. UTC, we opened an investigation and started diving into this signal. While connecting to a penetration testing website is not necessarily a problem, it may be a good signal that someone here is trying to abuse the system, whether an attacker or a security researcher. Looking into it may yield interesting results. At first, we focus on all details we can get around the alert. What is the domain that was targeted? What is the Synthetics test programmed to do? Does any of the data around this test look anomalous? These elements will allow us to first triage if we're facing what looks like a sophisticated attack or an obvious bug bounty type of activity. The second step is to dig into the malicious test owner's account. What users belong to this org? Do they belong to any other org? What are the tests exactly doing? The goal is to potentially uncover all the targets of the attack and leave no stones unturned. Looking at the handle of the users, it seems pretty clear that the activity on the account is not normal and that they are attempting to abuse the platform. Some of the handles suggest attempts of template injection or SQL injections. Amongst the other Synthetics tests were some that were trying to access local IPs such as 169.254, 169.254, which in many cloud providers will reference the local metadata service. Those IPs are already blocked by our system, so this attack was not successful. With the information we have so far, the attack path starts to become clearer. The threat actor created a malicious Synthetics account, used it to perform reconnaissance, attempt SQL injections, or other types of attacks. Through the tentative to access metadata services, it was pretty clear that they were also trying to access our cloud infrastructure, as well as our Kubernetes environment. At 5:50 p.m., we start wrapping up what we learned from our investigation. We see that the underlying org has been created in 2019 and does not have any recent activity or logins. Those connections are old, but they were detected by activating the network monitoring from Datadog. The org is not registered as a bug bounty org, but its activity looks very similar to one of a security researcher. At 6:44 p.m., we've gathered enough data and have a good understanding of what happened. The user tried to use the Synthetics product to perform reconnaissance, looking for a vulnerability. Out of the different attempts, none seemed successful. Considering this org has an abnormal usage of the platform and is a trial account, we decided to disable the org, which in turn will deactivate users and the underlying test to stop the activity. This activity is not a normal activity on our platform, and the org status prompted us to disable the org altogether. Finally, we continue to briefly investigate the attack attempts we've detected. None of them were successful. At 7:05 p.m., we decided to close our investigation. So, what did we learn? In detection engineering, there is a constant push and pull when writing rules between signal and noise. If an alert is too noisy, it is often ignored, or worse, wastes engineering time. In the case of attempted attacks as an indicator, we see that this signal is one worth revisiting. Earlier in the presentation, we discussed the new feature ASM Protect and its capability to automatically block threats across systems in your environment using the same rule logic you use to write detections. We hope that attempted attacks plus automatic blocking is a tool you can use to decrease the noise, save time, and stay safe. With that, I'll hand it back to Anthony to share just a little bit more on how we think about detection across the different parts of the cloud. Anthony?
Thanks, Jules. Our last C of cloud native security today is cloud. Cloud's going to be the largest of these abstractions and where the most blind spots exist for us to detect threats in our environments today. Cloud encompasses everything that enables us to build highly scalable applications like we do today. This includes the cloud identity and access management that ultimately facilitates and hooks into everything we do in the cloud. The SaaS applications we use day to day to enable our builds, or even collaboration tools such as Slack or Gmail. Most importantly, this layer includes our cloud control plane, which is incredibly powerful. Without the right identity hygiene, accidental exposure of highly permissive access keys can give attackers full control over our cloud footprint. Now, let's look at a real threat in Cloud SIEM, which is unfortunately common across our cloud environments today. Here, we can see an opportunistic attacker using a compromised AWS access key. This attack is easier to spot because the attacker is using that onion router network, anonymizing network that we mentioned earlier. This is a common tactic used by attackers to hide the source of their activities. Additionally, at a glance, we know this is a permanent IAM user access key that will require remediation effort to fix. But first, we want to understand what the attacker was able to accomplish with the access key. A key that was provisioned with a more administrative policy could be extremely problematic for us. If we use our Investigator app, we're able to very quickly visualize the process of reviewing all of those AWS CloudTrail logs to give us a quick insight into what happened. We can see the attacker was interested in the SES service, which allows bulk mail sending in AWS. Fortunately, we see failed API calls against those service endpoints, which gives us some relief that they're unlikely to achieve their objective. In this instance, that objective was to send mass spam email campaigns from your AWS account. The threat we just reviewed was a part of a greater attack campaign to compromise as many AWS accounts for abuse as possible. Unfortunately, there's limitations to real-time threat detection of AWS CloudTrail logs. We may not always have those logs available, or perhaps we want to observe potential compromise that occurred outside of the time bounds of our logging. This is where we can hunt for those indicators of attack across our stateful infrastructure data for our public cloud resources. Here's how our security organization at Datadog is able to develop a Rego policy and our cloud security management platform. Rego is an industry standard language we use to evaluate millions of resources continuously every few minutes to identify previous or real-time compromises of cloud resources. Now, let me turn it over to Andrew to tie all of this together with a final demo of a threat that spans across the 4 C's and how our observability data can help make us quick decisions on remediating the threat.
Thanks, Anthony. You've heard from Camille, Anthony, and Jules on how Datadog helps with code, container, and cluster. Now I'll share how Datadog Cloud Security Management helps with the most impactful pivot, which is that cloud provider compromise. Having all of the observability context through a single lens lets us tell a complete story of a security incident incredibly rapidly. Let's take this finding, for example. Process arguments match cryptocurrency miner. This has a high impact both from a security perspective and a container perspective due to the fact that our container is downloading and executing an arbitrary binary. You can see that here. We can quickly move to a related signal and see that the situation could potentially be much worse. The web server, in this case, is now spawning a subprocess to obtain temporary credentials from the cluster. In order to know whether those credentials have been leveraged, normally we would need to scan through potentially thousands of CloudTrail logs in order to assess the impact. Within Datadog, though, I can leverage the Cloud SIM for that. We could filter to only high-severity security signals, but the most important signal for this is actually right on the home page. An EBS snapshot in this case was made public. EBS snapshots should ultimately never be exposed publicly. And last year, we added AWS Investigator, a new feature that with one click, we can jump into a graph of all of the actions the IAM principal took that's associated with the cluster, giving us that final piece of context to know exactly how impactful a single security incident is. In this case, the attacker successfully exfiltrated data through that EBS snapshot, but they also created a new IAM user to persist in the AWS environment. Those cluster credentials are only authorized for 12 hours by default, so the attacker was clearly interested in maintaining access to our cloud control plane. All the way from code, container, to cluster, and finally cloud, you've now seen it all. And with that, that's a wrap for this Security Observability Day. I want to personally thank you for joining us to hear all about the 4 C's, detections, and our latest feature, ASM Protect. We're happy to take audience questions now, and of course, after the questions, keep in mind that for more great security content, workshops, breakouts, and more, don't forget to join us in person for Datadog Dash, August 2nd and 3rd in San Francisco. All right, now we're going to take questions. I'll bring the relevant speakers on screen to get you the very best, most high-quality answer, and we have had a ton of engagement in the Q&A and in the chat, so thanks for that. There's no way we're going to have time to answer every single one. But the first speaker I'll actually bring back to the stage is Camille to answer the question, how exactly does the IP blocking work?
IP blocking in ASM leverages Datadog's remote configuration feeders. The list of IPs and user IDs to be blocked are synchronized with remote configuration, and then the Datadog libraries pull from this data store and block the IPs and malicious users at the request level. The data that is being sent and pulled from remote configuration is securely encrypted.
Thanks, Camille. Our next question is, I think, perhaps best directed to Anthony. Anthony, can we write our own custom threat detection rules inside of the Cloud SIM, and how easy do you think that is?
Yes, so on top of all of the out-of-box rules that are in Cloud SIM today, we have a very user-friendly rule editor in the UI that lets users edit default detection rules and write their own. And then the editor doesn't require you to learn any particular complex proprietary query language. And you can also manage these via Terraform as well.
Great, I'll take the next question, which is how can I track and audit my workflows? So the Datadog workflow product is relatively new, and it leverages the audit log product to list workflow runs and workflow statuses. So the great news is that for any automation that you build in Datadog workflows, you're able to leverage all the same things in the product that you're used to using. One more question here for Anthony. Can a customer complement their existing SIM with Datadog Cloud SIM?
So yes, you can. Datadog Cloud SIM detects threats in real time through a real-time streaming engine for all of the data in your production environment from the logs product. But this means you can cost effectively protect your cloud native environment, where the volume and cost grow exponentially. We also have APIs available as well as webhooks to forward all of those alerts from our Cloud SIEM into your own Cloud SIEM as well.
All right, and I think we'll make this actually our last question for today. And of course, if we didn't have time to get to your question on the webinar today, we will send out follow-up emails to better answer some of these questions. And the final question is, how often does CWS Agent check a threat? So the CWS Agent, in this case, does not actually check threats, but instead monitors kernel events, file modifications, and process executions using eBPF. So it's actually filtering for relevant behavior and then emitting that signal to Datadog. So detections are near real time. With that, I think we'll go ahead and wrap it up here. Thanks again for being with us today, and we certainly hope to see you at Datadog Dash.